Hello, everyone, again. Let's keep talking about the Halliday and Resnick book, 10th edition. Let's talk about chapter 31, Electromagnetic Oscillations and Alternating Current. Let's take a look at problem number 69, and then this is a chapter where I've done, with the help of the great answer key and the help of the great book and everything that's going on here, I was able to look at a good number of problems here, and they're all going to scroll at the end. Right now, let's just take a look at this one problem. We may do another one as well, but let's just do this problem right here. Problem number 69 from chapter 31, Electromagnetic Oscillations and Alternating Current. Many problems are going to scroll at the end of this video from chapter 31. It was the opportunity arose to be able to do numerous problems there, and so they'll be there for you at the very end. You can see as they're scrolling. Again, this is from the Halliday and Resnick book, 10th edition. Problem number 69 from chapter 31 is saying a generator of frequency 3000 hertz drives a series RLC circuit with an EMF amplitude of 120 volts. The resistance is 40 ohms, the capacitance is 1.6 microfarads, and the inductance is 850 microhenries. What are the phase constant so here we go, ABC. What are the phase constant in radians? B, the current amplitude. Is the circuit capacitive, inductive, or in resonance? So let's see what we can say here, guys. There's a number of things they write here. Let's just kind of get a few of the things that they gave us. Let's get them under control there. It is an RLC circuit. It's a series RLC circuit. And the EMF amplitude, the EMF max, that's the amplitude, 120 volts. The resistance is 40 ohms. The capacitance is 1.6. See here, guys. Right, the capacitance is 1.60 microfarads. 1.60 microfarads is 1.6 times 10 to the negative 6 farads. The inductance is 850 microhenries. What are A, the phase constant in radians, and B, the current amplitude, and C, is the circuit capacitive, inductive, or in resonance? So let's see what we can do here, guys. It gave us a number of things that should be pretty useful to us. See how they're... Again, if in the answer key itself, they tend to, they tend to look at the significant figures play a big role in how they're giving the answers. Typically, when I teach the stuff, it's when we need to do so, we do. But the main thing is just get the answer right. But let's follow closely to what they're doing, and we'll kind of take it from there. We know a bunch of other things that kind of are staying in mind regarding this. Down the road, we're going to need to be cognizant of what the omega is. Omega is 2 pi f, and in this process, they told us what f was. I think it was 300 I'm sorry, 3,000, I believe. Make sure we're talking, yeah, 3,000 hertz drives that. And so to find omega, you got to make the right move. Obviously, just plugging in F being 3,000 hertz. 3,000 hertz right here, 2 pi times 3,000 hertz will give you the omega, and we can proceed from there. Well, why is that so important? As we know, it's important because if you want to talk about the inductive reactance, X sub L, that's omega L. If you want to talk about the capacitive reactance, that's 1 over omega C. So omega sub C is omega sub C is 1 over omega C. Omega sub L is omega L, and you better find out what omega is to be able to find out, to be able to do, I mean, we already know this. They flat out gave us this. We're going to have to use the C and the L to find X sub C and X sub L respectively. And that's essentially the argument, or much of the argument that we need to try to make sense out of some of this stuff. So let me erase this. Let's give ourselves a little bit of room and let's see what we can say. Okay, there's a lot of stuff there, but I mean, they give us all the data that we need to pull this whole thing off. Again, it's A, B, C. The parts are A, B, and C. You know, what are A, the phase constant, in radians? Well, based on what we've been talking about, if we're going to look at it in that direction, you're going to say that the tan, regarding the phase constant in radians, just make sure you have it set to radians, tan phi is this right here, XL minus XC over R. Give you the angle between so you're doing something like this, you're actually finding, just see here what I can say here, try to give a little bit of clarification. The angle between the total impedance and the resistance is going to be what's going to be happening in this regard. At this point, you're simply taking the inverse tangent in radians. I mean, if you get it in degrees, you can convert it to radians, certainly, so that's not an issue. You've got this. You've got this. You know, the way the whole process is proceeding, you're obviously, you know, when you're doing this, and I didn't really rigorously show it too much in the notes on this particular problem, but, you know, indeed, R is R. Not much to be done there, guys. R is R. XL is omega L. XC is 1 over omega C. And that's it. I mean, that's the whole story. So you can basically, I mean, we'll just right now, let's bypass the formal calculations. I think it's pretty clear what we have to do, and when we do it, we're going to get the answer that we need. We're given, you know, the maximum, the amplitude of the EMF in this alternating, where alternating current is taking place in this RLC circuit, where the alternating current is taking place, there's a maximum amplitude, a minimum amplitude, and et cetera, et cetera. E sub m, the maximum, the amplitude, the maximum voltage that we're going to have in this circuit, the amplitude of the EMF is, the amplitude of the EMF is E sub m is 120 volts. Omega is what we're using in X sub L and X sub C. So when we do it, let's just make sure. X sub L, X sub C. So omega equals 2 times pi times F. 2 pi F. Omega equals 2 pi F. That's 2 pi. Here's F. 3,000. 2 pi times 3,000. There's your omega. What's X sub L going to be? It's going to be 2 pi times, well, what's X sub L going to be? It's going to be omega L. It's going to be 2 pi times 3,000 times L, and L is 850 times 10 to the negative 6. Get an answer. X sub C is going to be 1 over the product, 2 pi times 3,000 times 1.6 times 10 to the negative 6. The reciprocal of that product, 1 over that, 1 over that will give you X sub C. Oh, they already gave it to you. Everybody's in the units of ohms, so that's not going to be an issue. You plug in all the values that you're supposed to get, and at the end of the day, you should get, and again, it's depending on how, if you're using significant figures or not. I think they may be using significant figures on this one. The big thing is, do we have the procedure down to get this answer? That's A. B, they're asking what is the maximum. What is the phase constant in radians? That was A. B, so what are the phase constant in radians? And B, the current amplitude. The current amplitude is pretty straightforward stuff. I mean, you're basically going to go, regarding the circumstances in which we find ourselves, you're simply saying the current amplitude is I max, and I max will arise from the electromotive force, maximum value it can have, divided by the total impedance. The impedance is, based on what we've seen, based on the figures we've seen, guys, you're looking at that situation. That's going to be the impedance. So what are we doing? Well, you saw how we calculated X sub L. You saw how we calculated X sub C. Do the subtraction here, get an answer, and square it. Then add that to R squared. When you got that answer, so in other words, this quantity, the difference between X sub L and X sub C, the quantity X sub L minus X sub C squared plus R squared, get an answer, get the square root of that entire answer, and that's the impedance, and that'll be in ohms. Obviously, if this is very large, it is not going to allow for there to be a very large maximum current. Okay. Well, anyway, we already know this is the maximum voltage is 120 volts. Z is whatever we calculate here, 120 volts divided by this. At the end of the day, the I, or the I max, I don't know how I wrote it. For some reason, I may not have even put a max on that. But there it is. I mean, it's really they're asking for the maximum. It is the I just wrote I. In the notes I wrote I mean, it is max. What is the current amplitude? What is the maximum? What is the current amplitude? I just called it I, but I max is a little more explicit about the whole situation. Well, again, plug in all the numbers, do what you have to do, and at the end of the day, you should be getting this. 0.288 amps for the Imax. Like I said in the notes, I got it written simply as I, but it is an amplitude. It is the max that would be possible in these circumstances. The impedance kind of runs the show on that. What would that amplitude be if the circuit were in resonance? If it were in resonance, if the XL and the XC were equal, if the XL and XC were equal, XL minus XC is 0. 0 squared is 0. Just got R squared. The square root of R squared is R. The Z would be R. Then you'd be taking, the Z would be R, and the R is 40 ohms, and the max right here, the maximum EMF, the maximum amplitude is 120. So 120 divided by 40 ohms, it'd be 3 amps. Wow, there's a significant difference looking at that. I mean, it's rather surprising how much it's cutting that down. And like I said, I don't believe I have the calculator on me right here. Maybe I do. Actually, I don't. But that's quite a difference, guys. I mean, we're talking about, you can even see it, give our quote-unquote gut feeling for this whole thing, I guess you could say. What kind of numbers are you talking about here? If, like I said, if this was in resonance, it would behave as though the XL and XC weren't there, in a sense, as far as the maximum current is concerned for what's going on here. You'd be talking about a situation of X sub L, X sub C. If X sub L and X sub C were equal to each other, that'd be 0. 0 squared is 0. R squared, the square root of R squared is R. Yeah, you're talking about 120 divided by 40. That's 3 amps. That's off by a factor of like, it's 10 times more maximum current you would have if this wasn't going on. Really? Okay, yeah, that must be quite a big number there. I mean, if you're talking about something like that, we're talking about Z. You got the 120 here for that to even happen. How are you going to get somebody to be 3/10 of that? Trying to think of a good way to, it'd be like, I don't know, this thing's probably in the ball. It sounds like it's in the ballpark. Just looking at it, Z would be in the ballpark of 400 ohms. Well, gee, that's a lot. I mean, 400 ohms, is that for real? Let's see. I mean, it's just, at first glance, it just doesn't, but I mean, there's a lot going on here. It's 2 pi F. This is about 6 point something times this. 6 point something times 3,000, that's about 20, let's put it in the ballpark of 20,000. This right here is 6. Forgive me here. Let's just see here. Yeah, right. I mean, 2 times pi is 6 point something times 3,000. Let's put it in the ballpark of 20,000. Omega is about 20,000. 20,000 times L. This right here. 20,000 times L would be 20,000, 200, just try to get a ballpark idea here, guys. 20,000, 200,000. Let's see here. Yeah, 20,000, 200,000, 8.5 times 2 million. That's about 17 million right there. That's huge. It's a big number, 17 million. On this end, so about 17 million for the answer here. Yeah, 17 million times 10 to the negative 6 is 17. Okay. X sub L is about 17. X sub C is 1 over all this. Let's see what we can say here. That's 17. On the other one right here, this right here would be 20,000 times this is 32,000. 32,000 is 3.2 times 10 to the 4. Multiply with this, that's 3.2 times 10 to the negative 2. That's 100 divided by that. This comes out to about 30. So X sub C is about 30 ohms. This is about 17 ohms. This is more capacitive. Okay, 30 minus 17 is 13. In the ballpark, 13, right? So let's see here. I mean, we're talking about 17 minus 30 something, you know. We'll see exactly what it would be. I mean, but we're just rough estimates here, guys. 17 minus 30 is negative 13. Negative 13 squared is 169. 169 plus there's got to be something here, guys. I'm just, for some reason, I'm thinking, I'm not very confident with the answers I'm getting here. We're putting this at about 20,000, 32,000. 30, 17, 169. I'm almost not believing the answers are given, to be honest with you. But you got this. Right, and like I said, my guess was about right. I said about 30. They said 33 for the capacitive circuit. That's X sub L. I'm having a little bit of a hard time believing some of the numbers they're getting here, guys. But let me just look this up, guys. Forgive me here. I just want to make sure. Right, they're given, I have no idea where that answer is coming from. Right, it's just not the right answer. It makes sense that it would not be the right answer. It would have been 3 amps on the, you know, so I'll have that, I'll correct that. I'll have my, we'll correct that. That's not going to be an issue. What we're getting here is, right. Yeah, across the board, they're just not giving good answers here, and that's I'm going to throw that on me. I mean, for some reason, perhaps some other place that we were looking at it. When you actually do this, guys, it's going to be a little different dynamic, and this is a little more believable. What's going on here? Got to remember, this is. Let's be careful here. Let's definitely be careful. Again, the numbers, I told you the numbers were unbelievable. I don't have the calculator on me, but what I was able to do and what everybody else is able to do, if they look at this in their head and try to get approximations, you're talking about this being in the ballpark of 17 ohms and this being in the ballpark of 30 ohms. Well, it turns out that it turns out, let's go there. X sub L I said was going to be in the ballpark. X sub L I said was going to be in the ballpark of 17 ohms. It's actually 16.022. And we saw the games we played with, yeah, don't even go here. Don't even go with that. Somewhere this is not on the mark. Perhaps the key was off in one place, but on in the other. And we said this one was going to be in the ballpark of 30 ohms, and it turns out it's 33.157. So who knows? I'm not... That's either on me or on the key that I followed very closely, guys, without really verifying the numbers. When we look at the numbers don't work. So be aware of that. I mean, that's what we're saying. And again, our guess was just doing the stuff in our head, about 17, about 30. Well, this is much closer to the exact answer. Well, now we said the very, very max that it would be if these guys were equal to each other, you subtract them, you get 0. 0 squared is 0. You're getting the square root of r squared. The square root of 40 squared is 40. Put a 40 here, put 120 here. 120 divided by 40 is 3 amps. True. Well, this isn't going to allow for that to happen. You're going to put the 33.157, you're going to put in for X sub C. The 16.022 ohms you're going to put in for X sub L. So, forgive me, for X sub C, you're going to put 33.157 ohms, and for X sub L, you're going to put 16.022 ohms. If you go X sub L minus X sub C, this is about 16, this is about 33. 16 minus 33 is negative 17. If you take about 16, about 33, 16 minus 33 is negative 17. Negative 17 squared is 289. R squared is 40 squared. That's 1600. Yeah, it shouldn't have been that far off, you guys. So when you do this, you get 1889. Ballpark idea, 1889. Get the square root of that, and you're going to get Z. Well, look, we were saying if it was in resonance, it would be 40 squared, which is 1600. The square root of 1600 is 40. 120, the max E, divided by the R, because these guys, let's say if it was in resonance, they'd be equal. Well, they're not equal. The circuit's not in resonance. But if it was, you'd go 40 squared to get 1600. The square root of 1600 is 40. 120 for the max EMF. 120 divided by 120 divided by 40 is 3 amps. If you took 1600 squared. This is not, forgive me, if you took 40 squared, the square root of 40 squared is 40. Well, 40 squared is 1600. The square root of 1600 is 40. This is going to be more than 40. You could just ballpark idea of where the whole thing would go when you're doing something like that, So you're saying, we'll cross every bridge as we need to get to it, guys, but as you do something like this, you're saying, well, what would that be? What's a good, well, it's got to be more than 40, because if you square 40, you only get 1600. If you square 50, you get 2500. It's a great day not to bring a calculator, right? I mean, so if you actually do this, you know, what do you got when it actually, you know, when you actually do it? So you got, you're going to get 225. Right here, you're going to get 1800. No, that's still too big. I mean, let's get somewhere in the ballpark of this thing just to get the answers believable. I was a little surprised at this. I'm not sure how I did it. I may have just looked at something that was done in the instructor solution manual, and it's going to be great most of the time. On occasion, mistakes get made. But again, we caught it, and let's kind of see here. Let's go here. Maybe somewhere around like 42 if you multiply it and see what happens here, right? See what we can say here. You'd get 84, and on this end, you'd get 1680. A lot closer. I got a feeling 3 might do the trick, pretty close. So let's do it. Let's get here. Well, this is what you do if you don't have a calculator. I guess you try to get a gut feeling. Now, we did get some pretty good gut feelings here. They were far from perfect. Again, the guess was 17 here and 30 here. True answer was 16 something rather than 17 and 33 something rather than 30. We got into the ballpark, which didn't make too much of what, you know, so we were able to catch what was kind of going wrong, which is a very important thing. So you get an idea, a number sense is really important in this regard. We do this, and let me just try to see what I can say here, guys, really quickly if I could. So you go here, you get 129, and over here you get 1720. That's 1849. That's pretty good. That's pretty close. Yeah, already 43 or so going into 120. You know, it's not quite, so it's a little bit more than that, you know. For the 189, you're off at 40, so it's going to be a little bit more than that, like, you know, let's say 40.5 or something like that when you do it. But let me quickly just look if 43.5 would actually work pretty good. 43.5 here, 43.5 here. The 0.5 is 21.5, 21.5. That is 43, yeah, not bad. About 43.4 or 43.5, somewhere in that ballpark. Yeah, I mean, maybe a little on the off side, but like a guess to say here, again, when we're going in a very rudimentary sense, to see where that's coming from, guys, let's see where this thing goes, and let's see where the answer is. The answer was not, our setup here was right, somewhere the math went wrong. Either I looked at the wrong thing, which easily could have happened, or I simply did it wrong, or the people that did the instructor solution manual may have made a mistake as well. I'm not looking at, I don't have it in front of me now to look at it, but everything's fine where we're at. What's going on here when you're saying something like this? If you were looking at 120 and you're dividing it by, let's say, 43.4 or so, you know, I guess there's a lot you can say. I mean, here it is. Go over a little bit. You got that. 400 something going into here. If it was 400, it'd go in 3 times. Yeah, you better believe it'd go in 3 times because it'd be a 40. If it was 3 times, it'd be the 3 amps that would be happening if it was in resonance. It's not quite going to happen, but I'll tell you what I'm going to do. You go here, and you got 868. Right, and that's 132 and 200 is 332. Correct. Here's that. Bring a 0 down. This is going to go in here almost 8 times. You know, again, we kind of, the way we did it here, let's just see where it goes here. Ballpark idea, darn, it comes pretty close to this, you know, for an answer there. You know, we can look at it, see how far off it's going to be. I think it's going to fall. It's going to overshoot it a little bit, but let's just see for the heck of it. Overshot it a little bit. So maybe with a smaller decimal here, we're in good shape. But it's getting to the ballpark of this. It's certainly not man, it's certainly not, we were saying, you know, we said earlier, 0.288. Got to be some kind of a, as we had seen it here, let's see here. Here it is. Yeah, 2.7. Yeah, it's going a little bit less than that. For problem number 69, it's saying 2.76 amps. It's going close to 8, but it's going to fall short of it. Yeah, it's going short of it. It's going to be, you know, an 8 right here, a 7 right there, and kind of close to 6. I mean, you knock it out, it should come in the ballpark of it. Again, these are just guesses, guys, not having the calculator, but the real big thing under consideration is, yeah, this is not, I have no idea where that came from. So luckily we caught it. The consideration to give here, the easiest thing to look at sometimes. Yeah, so for B, yeah, it shouldn't be too far away from 3 amps, and it's not. Absolutely true. Yeah, believable based on everything. Well, that kind of, everything, you know, a lot of wrenches get thrown in this, but I guess you could say all's well that ends well. We caught it in the middle of a presentation, but nonetheless, we caught it. And then you say, okay, well, what do you want to say? Well, let's see how this phi is going to work out here. Okay, we got it, and let's figure out where it's at. You're looking at a situation where it's phi is going to be the inverse. Again, we got to just call everything into question a little bit when we're doing this, some of this stuff. Omega L minus, forgive me. Yeah, right. You got XL minus XC, which is omega L minus 1 over omega C. Right, and then this is really the thing that really should have stood out more than anything. The XL was 16.022 minus, that's the XL, that's the that's the XL, that's the omega L, and that's 16.022. The XC, which is 1 over omega C, is 33.157. Okay, we've already been down this road, guy. That's a negative answer. R is 40. It's about a negative 17 over 40. Already we know this is going in quote unquote a direction that's going to be yielding a negative theta. Forgive me, it's going to be yielding a negative phi when we do it. So yeah, that's believable as well. When you look at something like this, let's try to look here and say if this is 40, we try to make that, if that's 40, you know, if this is 40 and the XL, if the bottom thing is 40 and the XL minus XC is like negative 17 or so, a little more than negative 17 actually. If that's 40, negative 17 is not quite half as long, but it's right here. And there's your phi. Well, if they were right on top of each other, the phi would be 0 radians. If the r and the xl minus xc and the xl minus xc, that's going to be a negative answer. But if the xl minus xc was as big as the r, you'd have an isosceles right triangle, and an isosceles right triangle has an angle of 45 degrees. 45 degrees is pi over 4. So it would be a negative. So if it was negative, if this is positive 40 and down here we're negative 40, negative 40 divided by positive 40 is negative 1. The inverse tangent of negative 1 would be a negative pi over 4, negative 45 degrees. Well, that's about 3/4. That's about negative 0.75. Well, it ain't going to go down. It's not going to go that far down, negative 0.8 or so. It's not as much negative as negative 0.8, and this guy's not, this one right here, this one right here is not this far down to give you pi over 4, to give you negative pi over 4, which we could say is about negative 0.8 or so. It's 3.14 divided by 4. We'll say negative 0.8 or so. Negative 0.8 right here, 0 right here, well, this is between 0 and negative 0.8, but it's going to be some kind of a negative number. Well, like I said, I just don't think I have a calculator, guys. I mean, you can always verify all of this, actually, but did not bring one with me. I was really confident with the notes, and most of the time, I'm confident with the notes for good reason. I mean, there's just great resources, the instructor's solutions manual, and then what I'm doing, hopefully it's meticulous enough and we're getting the right answers and stuff, but in this case, I guess we had to double check on it. You know it's not going to be as far down as this. You know, it's not as far down as something like that, like where that, if that were, I can't even make it big enough, like down that way. You know it's not that, and you know it's not this, and it's between. Well, that's about a negative 0.8 radians going this way, negative 0.8 radians, and this is 0 radians. Between 0 and negative 0.8 radians is somewhere where it's going to be. When you do the inverse and do it carefully, right, we are saying negative 0.405 radians. Negative 0.405 radians. And yeah, so there's A, there's B. What kind of circuit is this? Well, which one has the bigger impedance? X sub C or X sub L? X sub C does. So that's a capacitive, this is a capacitive circuit. And that, you know, like I said, you'll see it there, how it's written in the notes. Because X sub C is bigger than X sub L, right here, you're looking at it, because X sub C is greater than X sub L, for C, it's a capacitive circuit. All right, I mean, just, yeah, let's watch out. The big thing is watch out. So we're looking at this, guys. We'll make sure we have it straight when the stuff is scrolling. And there it is. That'll be up there. So let's see what we can say on that. Yeah, as simple as that. Okay, that was problem number 69. Let's look at problem number 82 very quickly regarding this. And like I said, guys, sometimes, again, the way that the answer key is going to depict things sometimes, almost always, in the instructor solutions manuals that you find, and then that I would find as a teacher, and that you would find in the student solutions manuals, the process is almost for sure always well thought out. Some sort of arithmetic error, some sort of calculation error can easily occur even when the entire thought process is correct. There was nothing wrong with any of the thought process here. The calculations were off, and we caught them, fortunately. Calculations were off, and we caught them, fortunately. Let's look at problem number 82. All right, so what we have here, very important to question what's going on. We know enough. We have enough mathematical savvy and enough number sense. Even without a calculator, we can catch something that's a little bit absurd. Whoever did it, whether it was me or the answer key or whatever, it doesn't matter. We can double check our work. We make our own mistakes. We make plenty of our own mistakes. If we got a good feeling for some of the mathematics, if we hopefully have a decent feeling for much of the mathematics that's out there, and then our calculation skills, with or without a calculator, we can kind of get some kind of a number sense to get a ballpark idea of what's going on. We can pick up some absurd occurrences that can happen, that can accidentally happen. And we did that here. We caught it. All right. We caught it and we gave the right answers. All right, for problem 82, chapter 31, a 1.50 for problem number 82, a 1.50 millihenry inductor in an oscillating LC circuit stores a maximum energy of 10 microjoules. What is the maximum current? Should be very straightforward. Yeah, we know that formula. Let's find the maximum current. Let's solve for the maximum current. Let us multiply each side of this equation by 2, divide by L, and then square root both sides. Basically, you got I max squared by itself if you multiply by 2 on each side and divide by L. Square root each side. the square root of all that. Two is 2. They told us the U max was 10 microjoules. Let's keep the MKS system of units. To keep the MKS system of units, you better make sure you are using joules, watts, amps, coulombs, newtons, kilograms, etc., seconds, you know. And so the units got to be there. If the units aren't that way and they're saying micro something, nano something, pico something, milli something, etc., make the conversion and make sure that, you know, the microjoules are 10 times negative 6. You know, 10 microjoules is 10 times 10 to the negative 6 joules. Make sure you're using the units that are going to be working. Millihenries. Well, I want henries based on how they've defined it. So if it's that many millihenries, how many henries is that? Multiply by that. Again, what the heck? We made it this far and we caught enough. I don't see that this is something that's going to be a major problem for us, but let's just watch out. 2 times 10 is 20. 1.5 is 1.5. 1.5 goes in, 1.5 is 3 halves. 3 halves goes into 20. 40 divided by 3 times. 40 divided by 3 is 13.3 repeating, 13 and a third. Good enough. This divided by that is negative 6, negative 6 minus a negative 3. Negative 6 minus a negative 3 is negative 6 plus 3 is negative 3. We got 13.3 times 10 to the negative 3. That's 40 over 3. It's about 13.3. 40 over 3 times 10 to the negative 3 times 10 to the negative 3 is 1 over 1,000. That's 40 over 3 times 1 over 1,000. That's 40 over 3,000. That's 4 over 300. That's 1 over 75. The square root of 1 over 75 is in the ballpark of, you know, between 1 over 8 and 1 over 9. So about 0.125. So about between 0.1 and between 0.1 and 0.13. I'm thinking the answer, ballpark idea, somewhere between 0.1 and 0.13. Somewhere around there, the Imax is the guess. Well, if you're not, so already if I see something absurd, hey man, it's got to be between 0.1 and 0.13. Okay, this is believable. This is believable. And that's the answer they got. And again, we did a lot of that. Just now we did a lot of that. Right in our minds. We got some ballpark ideas. We got 1 over 75. Wait, what's 1 over 75? Well, when I played all the game here, that whole thing, and it came out exactly to that actually. The square root of 1 over 75 is greater than the square root of 1 over 81, and it's less than the square root of 1 over 64. Sure, 1 over 64 is bigger than 1 over 75, and 1 over 75 is bigger. You know, 1 over 64 is bigger than 1 over 75, and 1 over 75 is bigger than 1 over 81. The square root of 1 over 81 is 1/9. Don't know what this one is, but I'm trying to get some ballpark idea so I don't get some absurd answer. The square root of 1 over 64 is 1/8. We're getting an answer here. 1 over 9 is about 0.111, a whole bunch of ones, right? Let me go 3 ones right there. And 1 over 8 is 0.125. And we're thinking the square root of 1 over 75 should be greater than 0.11, should be greater than 0.111 and should be less than 0.125. Well, it turns out it is. It's a little bigger than 0.11. It's a little bigger than 0.111 and it's smaller than 0.125. I believe it. We didn't even use a calculator. It's an idea of getting a gut feeling of what's going on sometimes just to catch yourself. We can think on our feet and catch something. Catch a mistake that we ourselves make or that somebody else makes or regardless. We can catch a mistake and get an idea of where we are so we can believe what we're saying. Okay, that is it. I will have problem number 69 in the notes. I'll have my, as I've done in the past, I'll have some of the great people in the IT, they'll straighten that out in the actual notes that I'm going to have scroll. So you're going to be fine. Thank you very much for your time. Take care.